Okay, so let us start with the 12th question of third chapter, Zettili second edition. So the question, we are given a Hamiltonian H and an operator A. Okay, and their matrix form is also given. And over here we have to see if the H and A commute, and if so, then we have to give the common eigenvectors of H and A. Then in the second question we have to see which among the following set of operators, so these are the different set of operators, form the complete set of commutating operators. Okay, now let us start with the first question. So I will try to refrain from going into matrix multiplication and seeing if they commute or not. So I will just gonna write the direct answers. So in the first question we have to show that H A equal to AH. So the matrix multiplication of H A is nothing but epsilon A naught minus n 0 0 0 0 2 0 7 0. Okay, and now the matrix multiplication, just a second. I had this mistake over here, it was 2. And similarly the matrix multiplication of AH gives us minus 10 0 0 0 0 2 0 2 0. So from these two we can say that HA is equal to AH, which implies H and A commute. Okay, so we have done the first part of first question. Now for the second part we have to find the basis of eigenvectors which are common in H and A both. Okay, so for that we have to calculate first the eigenvalue, and corresponding to those eigenvalue we have to find the eigenvector and for the both matrix, and then we have to see what are the common eigenvectors. Okay, so for H I have calculated the eigenvalue, which comes out to so there will be two eigenvalues. So the eigenvalues of H are minus 2 epsilon and epsilon. Okay, so these are the three eigenvalues for the given Hamiltonian, and the corresponding eigenvectors are 1 0 0 0 1 0 0 0 1. Similarly we have to find the same for A operator. Okay, please pardon me since I'm not going into the basic step of calculation of eigenvalues and eigenvectors, but yeah, these are the final answers that I have got. 5 0 0 0 2 0 2 0. So the eigenvalues are lambda prime. The eigenvalues are 5a0, 2a0 and 2a0, and corresponding eigenvectors are 1 0 0 0 0 1 0 1 0. Okay, so let me denote these eigenvectors as h1, h2, h3, a1, a2, a3. Now we can see that the basis of eigenvectors are common in these cases. So we can say that h1 was equal to a1, and h2 was equal to a3, and h3 was equal to a2. Alright, now we have to, so this particular question is also over. In the second part we have to see which is a set of operators that forms the complete set of commutating operators. Now if we have studied the complete set of commutating operators, so in the h and a operator, their eigenvalues are degenerate. So the set h cap and a cap both have degenerate eigenvalue, which implies they are not complete set of commutating operators. Now h and a cap commutes, we have seen that, which implies set h cap and a cap forms CSCO. Now in one of the properties of commutator, we can say that h square and a cap also commutes. This is from one of the properties of commutator, that if a and b are commutative, over here I am writing over here, if a and b commutes, then f of a and b, this function of some function of operator, and b also commutes. So from this I can say that h square and a also commutes, which implies h cap square and a also forms complete set of commutating operators. So I hope these two answers are quite satisfactory and helpful to you. So that is it for the particular question. So one thing I would like to say, that do go through the rigorous calculation of calculating the eigenvalue and eigenvectors for the H operator, or sorry, the H matrix and the A matrix. In the sense, they will surely help in analyzing what's actually going in the process. Okay, and I do recommend or read on the complete set of commutating operators. This is quite interesting, and I guess that's it. That's the maximum I can give into this video. So thank you for watching the video.